Chapter 4, Section 7 is a nice follow-up from the previous one, precipitation reactions. So before we were talking about how to predict them, and now we're going to talk about how to write them. And we just want to, we're going to introduce a couple terms here, which I haven't written down in front of you. They're on your worksheet, but you just want to step your way slowly through this. And I think you'll find that as long as you're very precise and very specific, it's hard to miss anything here. So how to write precipitation reactions. So first of all, consider the reaction of that we considered before, potassium carbonate. And you should take your time with this, right? Here's potassium. Okay. It's a group 1 metal. And here's carbonate. We looked this up in table 3.4. Carbonate. Potassium's got a +1 on it, so this must have a -2. Or it has a -2 because you memorized it. It's carbonate, right? Here's nickel. Here's chloride, right? Chloride's got a -1 on it, and there's 2 of them. So the nickel has a +2, right? So this is nickel 2 chloride. All right. So now what we've got, and I like what Tro did on page 150 with the different pictures. Let's consider it like that. We've got a potassium ion, another potassium ion, and a carbonate ion, and we mix them together, right? We get these 2 liquids and pour them together. We get nickel 2 and a chloride and another chloride, right? So suppose these are all floating around together in the beaker or whatever vessel you've got, right? So here's your little wavelets here. The bench is shaking around a lot, okay? So is potassium going to precipitate with carbonate? Well, no. How do you know? Well, because it says it's aqueous. You also know it's not going to precipitate because you look at the table 4.1, you look at the top row, and you see, oh, potassium is right there, and no exceptions, this does not precipitate. So potassium, I mean, we know it's not going to precipitate with carbonate, so let's put a big X there. Is it going to precipitate with chloride? Well, again, no exceptions, right? So no, that's not going to precipitate. What about nickel? Nickel is not going to precipitate with chloride because it came in already with chloride, so no, that's not going to happen. But it might precipitate with carbonate. We did this before. Nickel, carbonate. There's a +2 on here and a -2 on that, so this is going to go 1 to 1. We look on the table, look at the bottom row of table 4.1, and you see, hey, that's insoluble. That's going to become a solid. All right? So the way that this figure is also in your book. It's on page, oh, you know what? You know what? This is from a previous section. Sorry, this slide doesn't belong here. I'm going to show you anyway. We did this in the practice exercise. So, oops, where are we here? Okay. Right, we did that. Possible products are KCl and nickel carbonate. We just did this at the end of the slide at the presentation for 4.6, Tro 4.6. Okay, here's another one. Write out the possible products here. I know this belongs to a previous problem, but do it anyway. Pause the video and write it out. Possible products. Okay, is that what you wrote out? All right, good. All right, so let's go on to this. Those slides didn't even belong in this video, so pardon me. All right, let's move on to what does belong in this video, though. Let's now talk about what these reactions look like. So we did lead and chloride, a couple different reactions that we did. So look what happens here. Suppose that you've got lead to nitrate, aqueous, and potassium chloride, aqueous. What's that going to look like in solution? All right, well, as soon as it hits the water, the lead Goes off by itself, right? Because it's aqueous. Suppose this is all in the... Okay? And as soon as it's, when the nitrate goes off by itself, the potassium goes off by itself, the chloride does too, right? As soon as they hit the water. Now when we mix them, the lead sees the chloride across the room and says, hey, let's precipitate. Right, you see that? As soon as we mix them, lead sees chloride and says, didn't you know that I can precipitate beautifully? All right, it just takes the right counter ion. Okay, and that's what happens. Now, this is a nice way to write this out. It turns out this, if we write it out like this, let's see, lead to chloride solid plus potassium nitrate aqueous. This is how you're used to seeing reactions, right? Okay. Now, this is how you're used to seeing them. This is called, ready for this? I'm going to use a different color here. This is in your book, but I didn't write the word down here. This is called, I'm going to go with blue, a molecular equation. It's called a molecular equation. All right. Now, that is if we write it out like this. That's called a molecular equation. And that's how you're used to seeing things. Most common. Most common. Okay. Now, this is called a... Oops. No. How do you spell ionic? Ionic equation, right? Or a complete ionic equation, okay? And this is the way things really are underneath the surface, okay? And we'll introduce another term in a minute. Well, let me introduce it now. Then we have another term which is not shown here, where we take the aqueous. See how nitrate is aqueous here, and it looks the same over here. Nothing happens. Doesn't do anything. What about potassium? That's aqueous, and it's aqueous in the end also. Nothing happens. Okay. What we could do, I'm going to draw this in red again. What we could do then is we could say, well, what's really happening is lead. My handwriting is getting neater. Did you notice that? And chloride is precipitating to lead to chloride solid. Do you see you have a reaction here? This does not look the same in the end as it does in the beginning. Do you see that? And this now is called, and we need this term, it is called, back to blue, it is called net ionic equation. Okay? And it's called that because that contains all the information, the stuff that really happens. Okay? The potassium is doing nothing, and it's called a, well, you've got it here, spectator ion. You see that? They're just spectators, not doing anything at all. Just there keeping the charge, balanced. All right, let me erase these notes so we can look at the reaction on the bottom. Let's look at this one now. What color am I in? Let me go to red, okay? So what we have here is HCl, hydrochloric acid, which is aqueous, plus potassium hydroxide. Oh, I should make you name these. Produces, what's this? Oh, that's water. I recognize that. An old friend of mine. Plus, looks like we have potassium chloride is left, right? And that's aqueous. Okay? So that's that reaction written out completely. Now let's go here and say this, I called a minute ago, This is the molecular equation. Can you read my writing? Molecular equation. Okay? What's this called? Please, you need to guess. Don't just wait for me to say it. Pause the video and write it down. You'll learn it even better if you do that. Okay? So let me suppose you paused it because you're a cooperative. This is called the Ionic equation. Okay? Now let's consider getting rid of this. See, we've got spectator ions. You see chloride doesn't do anything here? It's the same in the beginning and the end. It's just a spectator. Hey, chloride, get off your butt. Chloride's doing nothing here. Oh my goodness, potassium. Nothing. Okay, so let's get rid of the spectator ions for the net ionic equation. Can you read my writing? Don't criticize. Okay. Go here. H plus aqueous plus chloride minus, right? Whoa. Sorry. That's a spectator. Nope, that's a spectator. Plus, here's the hydroxide. Aqueous produces water. Okay? This is not a precipitation reaction, by the way, because it's not a solid. Okay? But we do, it's very much like a precipitation reaction. Okay? So we have H plus and OH minus gives us water. And what do we call this kind of reaction? This is the net ionic equation. All right, because we got rid of all the spectators. They're not interesting to us. Okay, so now let's practice this. So consider the following precipitation reaction. So we relax, right? You don't need to know what this stuff is. I want you to practice naming it, but we are going to practice naming it, but that's not what the question says. It just says consider it, and then write the complete ionic equation and the net ionic equation. Why don't we write the molecular equation? Right, in the previous slide, I showed you how to do 3 of them. The molecular equation, the ionic equation, and the net ionic equation. Why not the molecular equation? Well, because it's right here. That's right. It's given to us. Okay? So let's name these first. First of all, this is strontium. And I see that strontium is in group 2. And so I don't need to say, it's always going to be +2, right? So I don't need to say what its charge is. It's simply strontium chloride, and I really should say, watch this, aqueous strontium chloride plus, and what's this? Lithium phosphate, right? Produces, strontium phosphate. I'm doing more than I was asked to do in the question, okay? This is important for practice, okay? This is solid strontium phosphate and aqueous lithium chloride plus that other stuff, okay? All right, now write the complete ionic equation. So if this is aqueous, that means that strontium comes in as a 2+, and it's aqueous, and the chloride is not with it, right? And there's 2 of them. Okay? Is added to, it looks like there's 6 lithium ions. And they're aqueous. And it looks like there's 2 phosphate ions. PO4, 3-. Where are we here? And those are aqueous. Okay, It's not unusual to run out of space when we're doing the ionic equation, so I'm just going to do that. Come down here. And it looks like the strontium and the phosphate are together now, so we can't separate them. Right? They're together. They precipitated. Okay? Plus the lithium chloride, but they're aqueous, so they're not together. 6 lithium is still in solution. And the chlorides, which are still in solution. Looks like there's 6 of those too. Okay? So this is the complete ionic equation. Okay? Now to write the net ionic equation, what we're just going to do, I'm going to change colors here. I'm just going to go through here for the net, and I'm going to get rid of everything that doesn't change. The lithiums don't change. Oops, it was 6 of those, right? 2 of them in each one, but sorry. There were 3 here and 6 here, right? Can you see that? 3 strontiums and 3 times 2 chlorides. Okay, so the chlorides don't change. Okay, so it looks like I've got 3 strontium, 2 pluses, and they're aqueous in the beginning. Plus, I got rid of those, looks like 2 phosphates minus 3, they're aqueous in the beginning, and they precipitate to produce strontium phosphate. Okay, and this is the, oops, I thought I did that, net ionic equation. All right, this is gonna require some practice. I guess I say that a lot, don't I? I think it's always true. Okay, so that's it for section 4.7. In review, what we did here was we let me get a different color here. We introduced you. Well, you'd already seen molecular equations. We never called it anything. Okay. Molecular equations, complete ionic equations, right, and net ionic equations. Molecular equations are the way we usually see it. This is the most common. Okay? The complete ionic is what's really happening beneath the surface, right? Sounds a little spooky. Beneath the surface, and then this is what matters. Okay? That's the net ionic equation. And we use all 3 of them for different purposes, right? We use the molecular equation if we want to talk about it, about this, with the label said on the bottles that we mix together. We use the complete ionic equation if we want to think about what's going on. And we use the net ionic equation if we want to talk about just the net reaction of what really happens. Okay? Hope that's helpful.